Okay, so the previous video for here, if you didn't watch it, go back and watch it, explains just with the picture how we expect the resultant force of this object to look. Now we're going to do it all with numbers. Okay, so we have two forces and they want us to calculate the resultant force. The resultant force is the sum of all forces upon an object. Now, what have we learned about vectors up to this point? We've learned about three different ways to represent them. We can represent a vector in component form like this, which then results in being able to write linear combination form, which looks like that. But according to the information given in this problem, I don't have those. I don't have a linear representation of the run and the rise. That's what these are, right? I have the magnitude and I have the direction angle. We have a third way of representing vectors. Third way, did you catch that? Yeah, that's 4. We have a third way of representing a vector in terms of its magnitude and its force, its direction. And that's what we're going to lean on. So I'm going to call this, I'll try to keep my color coding proper here, right? I'm going to call this force vector 1 for no other reason. I like to draw that fancy little F symbol, okay? Force vector 1 has a magnitude of 40 pounds and it has a direction of 45. So this is the third option. This is the third way we learned that we can format what a vector looks like. Force vector 2 has a magnitude of 60 pounds and is pulling at an angle of 135 degrees. So it looks like this. All right. The resultant force is what I get, and I think I'll use black for this. The resultant force is the sum of force vector 1 and force vector 2. When we were learning about vector operations the first time around, again, let's review. When we were learning about, where was it? Here it was. Okay, when we were learning about vector operations before, we said it's really quite simple. When you want to add two vectors, you simply just add their two components. Okay, so if I want to add u and v in this instance, -3 plus 6 is 3, 2 plus -1 is 1, right? Pretty much common sense there in terms of finding their sums. So the same thing applies, even though these look different, even though these types of problems look different. If I want to add this force vector and this force vector, I need to add their horizontal components and their vertical components. They just look different, okay? So what I'm going to say is, how do we write this? Let's say for the resultant force, right? For the resultant force, what we're going to do is we're going to add the horizontal components, which are these two. It's not just this piece, because this 40 is on the outside. Scalar multiplication means we'd have to multiply this times this, okay, and multiply this here. So for the resultant force, actually, you know what might make more sense? Sorry, I'm going to pause this for a second. Let's rewrite force vector 1 in decimal form before I go any further, because that'll make a lot more sense than looking at all of this nonsense. Because keep in mind, this has a decimal value to it, right? You actually might remember what that's equal to from your work on the unit circle, which would be awesome, right? But I'm going to write force vector 1 in its decimal form instead of in this format. So force vector 1, 40 times the cosine of 45. I still got my Desmos window open, so I'm going to get that warmed up again. Here it is. 40 times the cosine of 45. Let's make sure we're in degree mode. Be careful there. Okay. 40 times the cosine of 45 is 28.28. So the horizontal component for force vector 1, 28.28. The vertical component is what I get when I do 40 times the sine of 45. So I want to get decimals for these, much easier to work with than these trig forms, right? So 40 times the sine of 45. I'm gonna cheat here a little bit. Oh, wouldn't you know it, 28.28. Maybe you were saying to yourself as I went off screen, but it's gonna be the same, Mr. Jackson, because the x-coordinate and the y-coordinate of a 45-degree angle are the same. They're both radical 2 over 2. I'm sure you were all thinking that. Yeah, right, of course, right? But we only spent like a month on that stuff, right? The cosine of 45 degrees is the x-coordinate at 45 degrees on the unit circle. I'm sorry to assume that you remember stuff that we covered in the past, but we did cover it, right? The sine of 45 degrees is radical 2 over 2. They're the same. That's why these are the same. All right. Now, for the second force vector, when we do 60 times the cosine of 135, what are we going to get for that? Let's do both of these at the same time so I don't have to keep jumping back and forth. Let's do 60 times the cosine of 135, and let's do 60 times the sine of 135. Negative 42.42, positive 42.42. For pretty much the same exact reasons, these were the same. The difference here is, 42.42, positive 42.42. So these are the components in decimal form, real number format, than what we had before. So to find the resultant force, I'm going to add these two forces together. And here's how I'm going to show that. I'm going to add these. So I'm just going to add straight down. Force vector 1 plus force vector 2 gives us the resultant force here. Negative 42.42, so 28.28. I would do this in my head, but I'm worried I'll make a mistake, and all of my thousands of YouTube subscribers will laugh at me. Negative 14.14. My adoring fans. Negative 14.14, and when I add these together, I think I can do that one. That's 70.70. Okay. So, the resultant force has these components. Here's the rub. This problem wasn't phrased in terms of the components of these forces, right? It was phrased in terms of their magnitude and direction angle. So what do you think we're going to do, right? We're going to finally, I know it's taken us a while to get to this point, but we're going to take these components and we're going to find the magnitude of the resultant force by taking the components. You guys remember the formula, right? The formula for magnitude, V1 squared plus V2 squared under the square root. So this is negative 14.14 squared plus 70.70 squared. Back to Desmos again. So we're going to take the square root of negative 14, squared plus 70.70, 7.7 really, squared. We get 72.10. 72.10, this is our magnitude. Right, 72.1, yes, 72.1. And since this is a magnitude measurement, and for forces, magnitude is pounds. Okay, now, before we go any further, let's verify that. 72 pounds worth of force. I suppose that makes sense, doesn't it? Because if this is 60 pounds, and we did this with the graph where we said this copied up to here and we got our resultant force that would look like that, that's longer than that. So it would make sense that the force that I got would be longer than this force, which would be much longer than that one. Okay. Now in terms of the direction angle, we know we can find the direction angle of a vector if we take the inverse tangent of V2 over V1. Okay? You know where this is headed. If you've been keeping track of everything up to this point, you know where this is headed. We're going to go back to here. We're going to hit our functions button because we have inverse tangent. We're We're going to take the inverse tangent of 7.7 over negative 14.14. We get negative 78. I'm going to say negative 78.7. Negative 78.7. If you put a box around this and you're like, yeah, that's what the formula said, so I'm good, then you've been missing the point all along. We got negative 78.7. Come back up here. The direction angle of a vector has to be measured from the positive x-axis in this direction. So are you telling me that an angle that starts here and swings like this, I'm going to make this red for the sake of contrast, that angle is negative 78 degrees? No. Okay. That's why I said maybe you saw where this was headed. This angle is past 90 degrees. I mean, the picture's not surgically accurate, but it's good enough, right? So we're past 90 degrees. Negative 78 degrees doesn't make any sense. What's the negative 78 degrees that we got? It's this reference angle over here, right? That's the 78 degree angle. We've seen this half a dozen times at this point. You can't trust what the formula tells you to be your final answer. We got this angle, which is negative 78.7 degrees. We're always finding a reference angle when we use this formula. So if this is negative 78.7 degrees, let's draw it down here so I don't have to keep switching back and forth. We got an angle of negative 78.7 degrees here, but we want this angle. So if that's 78.7, theta is really 180 minus 78.7, which is 101.3 degrees. That makes a lot more sense because we've passed that 90 degree threshold where it's straight vertical, right? And it's over here to the left. So this is the direction of the force of that object, and this is the amount of pounds it's moving, that force is moving in that direction.